All right, everyone, are we ready to start with the next tutorial? Cool. Yeah, so I prepared a little tutorial on visualization of ICESat-2 data and data discovery in Open Altimetry and Google Earth Engine. And it would be really great if you guys could actually try to follow along this tutorial while running the code, because I have a little activity at the end that I will hopefully get to, if there's enough time, where you would get to run some of that code yourself. All right, so let's get started. As I said, the idea is essentially to just try to find some interesting ICESat-2 data where we don't really know what's going on, get that into a Jupyter notebook, and then use Google Earth Engine to find some satellite imagery that's close in time with that overpass of ICESat-2, and visualize that in a way that makes more sense of the data. So to put it into some nice context. So to get started, here's just a few imports, and I'm hearing myself on my computer. This is a little weird. Okay. So we're just going to be using those standard libraries. They should all be on CryoCloud. And then what I'm importing to here is this data collector class from my helper script thing. So, first of all, I should probably tell you how to get there because I'm not in the right directory. So if you want to run this tutorial, you can go to the Hackweek 2023 directory that you have cloned, and you would navigate to book on the left. From there, go to tutorials, and then there's a folder that is data visualization here. So this is our directory for now, and to open this notebook that I'm running here, this is like the first notebook here, Open Altimetry Earth Engine, and that's the one I'm running here. So, right, imports. So there's this data collector class. This is something that I wrote that just helps doing some of the computations in the background. If you do want to see what's going on there, you can navigate to this folder and click this Python file, OA for Open Altimetry, and it just has a bunch of code that runs in data and plots it and everything, and we will get back to that in just a bit. But for now, you don't have to worry what's in there. Just if you're interested in using some of this code and modifying it yourself, you can find that here. All right, so to run stuff in this notebook, you need to be authenticated for Google Earth Engine. I hope some of you have managed to set that up, leading to the Hackweek. So if I run this box here, I think I'm already authenticated with Google Earth Engine, so I'll just add a little box here to show how this works. So you would authenticate yourself with EE authenticate. This should pop up if you're not authenticated running this box. And this just gives you a link that you can click. And that takes you to this Google Earth Engine side, shows you your account. As long as you've been successfully set up here, you can click Generate Token, and then it takes you through a few other things. I hope this works for me right now. Yep, there we go. And you just need to click through that, click Allow, and that should show you this code that you can copy, clicking on this copy button. Go back into your notebook, paste that into the verification code, and hit Enter, and that should say that it's successfully saved the authorization token. And from now on, you should not be able, it should not be necessary for you to run this again while you're on CryoCloud, because this token has been saved. All right. Now that we're hopefully all authenticated on Google Earth Engine, let's get started with some data. And we've already seen Open Altimetry just earlier, and let's say we just found some interesting data, but we don't really know what's going on here. So here on the right, there's ATL 06 plotted, and we have the two center tracks of this, and they just kind of erratically jump around, and we're curious about this. So I pasted a whole explanation of how I got to this data, but I'll demonstrate it here real quick. So if you navigate to Open Altimetry, it will take you to this page, and you can just browse ICESat-2 data. And that takes you to this interface that we've already seen. And there's a few things to notice here. So first, you can change the data products here up on the right. In this case, I'm going to be looking at Greenland, so I'm more interested in ATL06. So I can change that. Then another thing is you can change the map projection. So if you're interested in Antarctica or in the Arctic, you can change the map projection, and that will just flip the map to give you a better idea of the polar regions. Now, these are just like tracks that have data off the selected day, and it automatically jumps to the latest available data on Open Altimetry, which is for now only until October 2022. But I am actually interested in data from, I need to check this, August 2021. So on this calendar, I can flip through the months, and in this case, navigate to August 2021. And in this case, say I'm just interested in August 22, 2021, and this shows the available data here. So I can kind of scroll into the region that I'm interested in roughly. Let's say we want to look at the ice margin here. And we notice that it's pretty bad quality on the base map, but at some point these ground tracks, like all the available ground tracks, show up. So one more thing that I can change here is I can add this cloud button on the left, and that will just toggle to show MODIS imagery from that day. And now we get a lot better idea of what the data actually is from this day that we're looking at. So in this region, let's say there is a bunch of dark spots, and we're just interested in what these mean. And now this is a little bit laggy, so bear with me here. Now, if we're interested in some data, we can just click select a region up on the upper left and say we just want to look at one of these dark spots. So from here, we can click view elevation profile or view signal photons. Either of those takes you to this next page. And this is pretty much the data that I had displayed earlier. And so here's a few things that you can do. You can look at different data products. In this case, I already selected ATL06, but it also shows you ATL08, for example. So this is kind of weird too. There's some canopy apparently on the Greenland ice sheet here, and there's definitely some more things we could find out here. One thing that definitely helps is click on the photon heights, and this will take a little bit to load, but now we see some kind of weird data again. And from here, we kind of want to load this in a Jupyter notebook to look at that data a little bit more and find out more. So what we can do here is use the API, and that's fairly simple here. They give you an API URL from the data that you've looked at. You can just click on that, and it copies it to your clipboard. And if we now go back to this notebook, we can just copy paste this URL into this line. And if we run the cell, we've just specified that we're looking at this API URL, and we're interested in GT1R, which was the strong beam off that data here. So going from there, we're going to use this data collector class that I wrote. Essentially, this is just a utility function that initializes this and returns the API URL, the dates, the track number, and the latitude and longitude limits, and the beam that we specified. Same thing could work if we just specified those things individually. We can run the same function just with those inputs, and it shows that API URL that gets generated for you. One thing to note is just say it says ATL XX here, because that's just a placeholder for whichever data product you would want to look for. So from there, we can just request, call the method request data. That's something that I also wrote in the background, but essentially it just pulls this data from OpenAltimetry and tells us how many data points it found for each data product. And here we see there's only ATL03, ATL06, and ATL08 data. If we're looking into this data collector class or object now, here I'm just printing the variables. It has everything we had before, but it added on some data frames for the different data that just has like latitude, longitude, elevation, and some other parameters if for those data products where it makes sense. For example, ATL08 has canopy. So from there, we can go to just plotting our data in the notebook. And that's just a standard matplotlib code. It's a big block here, but I guess most of you are familiar with matplotlib. So this is just something to plot this data, throw it on a graph, and show all the different data products next to each other. Actually, here I've only plotted ATL06 and ATL08, which gets shown by OpenAltimetry at first, but we can add ATL03 as a point cloud. And now we have all these together on one single plot, which quite often helps. And so we see that the photon cloud for ATL03 kind of shows a flat surface here and then a curvy surface below. And the other data product, ATL06 and ATL08, can't really seem to decide where they want to go there. And that is kind of what Tyler pointed out, that these data products are just designed to find a singular surface. And in this case, they're just hopping erratically around because there's two. So from there, we can go and like save our figure just to make sure we save our progress and can show this to whoever asks us for data. And if this, oh no, this should just save this as a plot into our directory. And this is just an image file, so we have this saved here. All right. So this really doesn't tell us exactly what is going on. So we want to find out a little bit more about this this ground track. Oh, first of all, I totally forgot. I wrote all this code into a method too that kind of automatically adjusts your limits and everything. So you can just call this ICESat-2 data object and say plot data, and it just spits you out a figure just to make it faster. And somehow this figure is here twice now. So something that quite often helps, because we're plotting usually latitude versus elevation. It's not really intuitive what that means. Nobody ever says I walked like 1/10 of a latitude on this hike yesterday. So well, I haven't heard anyone. I don't know. That would be kind of fun. It's 11 kilometers or something. But yeah, so it would be fine to figure out how long is this ground track. And again, I just wrote a little helper function that just converts like endpoints of a line from latitude and longitude into a distance, geodesic distance. And if we run this, we see that the ground track is about 4.4 kilometers long. So that gives us a little bit more of an idea. This weird feature in the middle should be about half as long, like 2 kilometers. So now we really want to figure out what's going on there. And we're all visual people. It helps to have some images next to it. So it would be cool to find some imagery that was taken roughly when ICESat-2 passed over the spot. And Google Earth Engine is just a tool that's really helpful on there because it has tons of raster data, different satellite data. There's Landsat, Sentinel. There's tons of DMs. Lots of things that you can explore in their data collection. And if you just Google Earth Engine, it will take you to a long list of data products that are available there. And the nice thing about Google Earth Engine is that you can kind of query and use them all in a unified framework that makes it a little bit easier to pull together different data. So online, there's a code editor. So if you just go to code.googleearthengine something, then you will find that. And this is JavaScript. And because we're all Python people here, and most people probably aren't super comfortable with JavaScript. It would be nice to pull all this into our standard workflows in Jupyter Notebooks or Python. So for that, there's a Python API for Earth Engine that we imported with import EE. And there's also a package called GEE map that helps you just plot these Earth Engine objects on a map directly in Jupyter Notebooks. And we imported that earlier too. So to show ground track on a map, we would use this GEE map package. So here we can just start calling a map without anything else, and this just opens up an IPY leaflet map of the world. Now we want the ICESat-2 ground track on there, and we have to specify the coordinates reference system here. So we essentially just, in this case, I'm just taking the ATL08 latitude and longitude data, specify that this is in the latitude and longitude EPSG 4326 coordinate reference system, and then make an Earth Engine feature collection from this. And that essentially just tells us this is a feature collection in Earth Engine. It currently doesn't really live in our notebook, but it has access to it if we request it. So what we can do is just do map.addLayer and add that ground track feature. And now if we go back to the map, we see nothing. So that's not great, but we could remember that we were in Greenland, and there's a little green streak, little red streak actually in this case, where ICESat-2 passed over. There's easier way to do this. We can just calculate the center, latitude and longitude, and call map.setCenter. And now if we go back, we actually have this in the center here, and we can go in. So this is just a base map. Really doesn't tell us any much more about this ground track. So what we can do next is add a base map. There's multiple base maps in this package, or for an IPY leaflet. And in this case, we just take satellite imagery. We can, again, go back to our map. And this is pretty much what we saw in Google Earth Engine. If we zoom really close in, we have higher resolution imagery, but there just seems to be a weird crater. Not quite sure what's going on there. It's probably not imagery from when ICESat-2 was there, so it still doesn't tell us much more. So now it comes in Sentinel-2. This is like a constellation of so far just 2 satellites. There's more in the making, but they pass over every 5 days or so in most places of the Earth. And if you're in the high latitudes, it's scenes overlap, so you get even more data. So in Google Earth Engine, if you go to this catalog link, you can find all the different image collections that are there, and the Sentinel-2 one is just under Copernicus, Sentinel-2 surface reflectance harmonized. So we can just specify this as like our collection name. And so if we call this Earth Engine image collection on that name, it runs for a while for some reason. Okay. Essentially just tells us this is an Earth Engine image collection. It just refers to that. That is something that's a little bit annoying sometimes. Things run in Google Earth Engine, so we don't directly have access to this necessarily on our computer until we request it. Some interesting information we could request is how many images are there in total. So we could call collection.size and then print this, and it turns out that also does nothing. So this is still all internal in Google Earth Engine, and essentially just tells Google Earth Engine on the server side, here's a variable that we call number of scenes, and it refers to the size of this collection, but Google Earth Engine doesn't actually go through all the images and counts them until we actually need this for further computation or explicitly request this. And that's actually really helpful because, well, quite often we don't actually need to execute these things until they're really needed. So what you could do is do this collection.size and then call this getInfo function, and that forces Google Earth Engine to actually compute this thing and return it to you. If you did that on the entire Sentinel-2 collection, this would take quite a while. This is why we're not doing it, but I ran this when I started the tutorial, and there's over 19 million scenes. So we really don't want to sort through them manually. That would be a long hack week. So we can filter this image collection, and we could do this with any other collection that we find on Google Earth Engine in exactly the same manner. So if you're interested in Sentinel-1, for example, you would just change the name, and you could then do the same operations on this collection as we do here with Sentinel-2, pretty much. So to filter this, we first create a point in Google Earth Engine from our center, longitude, and latitude, and then we can call this filter bound functions, and that essentially just returns a collection that only intersects with that center point. And so now we can call this .size.getInfo thing, and now it runs a lot faster, and we're left with 2,700 something images. Still too many to really look at all of them. So we can look at images that are close in time to that ICESat-2 overpass. And here I'm just specifying this variable days buffer imagery. So I'm just saying like, okay, I'm looking at like plus or minus 6 days off that ICESat-2 overpass, and anything else I'm not interested in, because we really want to know what's going on at the time. So from there, this next cell is essentially just like juggling around a few different date formats. But essentially what it does is it just tells us that we're now looking for imagery from August 16 to August 28. And then we can call this filter date function with these two start and end dates. And now we're left with 34 images. So that's pretty good. We could actually start looking at those manually and not sit here for years. We'll just sort this collection by the start time or acquisition time, just so they're in order. So now we want to inspect this collection that we narrowed down to what we're interested in. So we can call this getInfo thing on the entire collection, and this just returns a dictionary. And if we look what's inside of this dictionary, we see there's like type, bands, ID, version, all these different things. One thing that sounds interesting is features in this case, because it's a feature collection. This is probably our images. So let's see how long this feature entry is, and it's 34. So each of these entries corresponds to one of our images that we've queried. So let's just pick the first one and see what we get, which information we get returned here. So if we're in there, it again returns a dictionary that says type, bands, version, and so on. So let's look just like at the idea of the first thing. And this returns this Copernicus and then like a name off a granule, essentially. So this is helpful. So we can get quite a bit of information out of all this collection. For example, we could also loop through all the bands and print their names. And this is just like the band names for Sentinel-2, which will come in handy later. So, properties could be helpful too, if we call that. There's a whole lot going on. But this is essentially like all the different metadata that we get with this image. And if you're interested in something very specific, you can kind of sift through that and just see what's relevant for you. For now, we'll just look at the granule ID, and now we can loop through our 34 features or images that we have here and just print their granule IDs. And so essentially, this is kind of nice. We have a list of granule IDs of Sentinel-2 that were acquired within 6 days of ICESat-2 passing over that particular location. So let's just add one of these to the map to see what it looks like. To add this to the map, we have to choose the red, green, and blue bands, because that's just how our eyes work. So we have to select band 4, 3, and 2, which correspond to red, green, and blue. We can specify some visualization parameters. The details aren't super important. And then just add that image to the map and show it on the map with the ground track. And now we get this map and there is clouds everywhere. Cool. We still don't know what's going on. So there's another step that we can take, and we can actually calculate how much the probability is along this ground track for clouds. And that should help us find some clear images that actually tell us what is going on. So there is a different collection on Google Earth that says Sentinel-2 cloud probability. It is a little bit annoying that it is a separate collection. So what we have to do is we have to merge the Sentinel-2 collection with this cloud probability collection to get good information on this. And I wrote a fairly long block of code here that does that. You don't really have to understand what's going on here very much, but it essentially does this filtering for us, and it merges the surface reflectance Sentinel-2 and the cloud probability into one data collection, and then it takes out the values of the cloud probability just along the ground track and takes the mean of that. So it tells us how much cloud probability is there actually in like a 100-meter buffer zone around our ground track, and adds that as a property to each image. So I need to run this cell to make this work. And now we can call that just like on our data, open altimetry data objects. And if we do that and then print all the returned Sentinel-2 granule IDs, we can also print this along track mean cloud probability. And here we see that the first image that we just randomly chose has a 90% cloud probability, and that's really not helpful for us. We don't want that. So we can just filter out any of those images that have too many clouds in them. And the way we do that is we just choose a maximum like threshold of the percentage of clouds along there, which I just chose to be 5 now. That's pretty aggressive, but I want a really clear image. And then we can filter this collection with this Earth Engine filter LT, which means less than, and call that on the ground track cloud probability. And if we filter this and then see how many images there are left in the collection, we're now actually just left with 4 cloud-free scenes. Something else that we should do is sort this collection by the time difference from the ICESat-2 overpass. And I just wrote this very small function here that calculates the time difference between the system, like acquisition time, and the time from open altimetry. One problem here is that open altimetry actually just provides dates and not the actual hours. So this is like plus or minus 12 hours for now. You could run very similar code on data that you actually downloaded from NSIDC, and then you could use the exact time there to make sure you only want acquisitions that are an hour apart or something. With open altimetry, unfortunately, right now, this is a little bit limited. But if we run this and sort it, we can then just print some more stats for our filtered collection. So essentially, we have these 4 granules. We have the along track mean cloud probability, and we have the difference between that acquisition and ICESat-2. And now our first image here has 1.3% clouds and is about a day or a good day before ICESat-2. So we can just take that first image and show it on a map. And finally, it worked. So after all this cloud filtering and fooling around in Google Earth Engine, we actually get a cloud-free image with our satellite track over it. And it was just, the image was taken a day before ICESat-2. So we can be fairly confident that this is actually what we're looking at. And now this is a melt lake. So what we looked at was actually bathymetry data, which most of you probably could have guessed after the earlier tutorial. So now we have this on this interactive map. And one thing that we want to do is, again, take that back into our computing environment in Jupyter so that we can make a nice plot for our publication or whatever we're working on. So one thing we can use here is this get download URL function in Google Earth Engine. And one drawback here is that the request size there is limited to a certain size. So if you do it just as is and download the data, you're kind of limited to images that are like not longer than maybe like 20 by 20 kilometers or something for Sentinel-2. It varies by the collection that you're looking at and what the resolution is. But at least for these small scale features, if we just apply it as is, it works. So we can here kind of just define a region of interest. This just buffers around our center point, and then make our image like an 8-bit RGB composite, and then call this get download URL function. And all this returns is this download URL. And if I clicked on it, it would just download the image for me. But we can also save it directly to the notebook with the requests library. And now it says it downloaded my satellite image.tiff, and this should appear somewhere here on the left. Yeah, there we go. And now this doesn't actually show anything. I guess it doesn't render in CryoCloud. So we can open this with raster.io. This is a fairly popular geospatial raster library for Python. And so we can open this file with raster.io. We imported it as Rio. And this is just a data set reader, but we can plot it in matplotlib with the .plot module, which I imported as Rio plot. And this will just show us a figure off our image. And now we're in our very trusted environment in Matplotlib and Python and Jupyter notebooks, and we can do all sorts of things with it. And the one thing that we're definitely interested in is showing the ground track of ICESat-2 on there. The one thing we have to change first is change the CRS, or coordinate reference system. So we use this warp transform module here, and we essentially specify that we're changing the coordinates from latitude and longitude to the CRS that we have in our image, because this is a geotiff. And then we can add this to the plot, and this just adds this line to the plot. So now we have a nice plot here. To put this all together, I again wrote a helper function into this OpenAltimetry data collector class, and it just says visualize Sentinel-2, and you can change some parameters there. There's like the max cloud probability that you could look at. There's how many days buffer you want to look around, and some other like visualization parameters that you can change if you see fit. And so now essentially I've taken all this code that I've presented so far and put it in this function. And you can run this in 3 lines by just copy pasting your OpenAltimetry URL, specifying a beam, and then just running this function. And now I don't know why my code isn't working. I probably messed around in the here, but either way, it looks like it's doing something. Okay, cool, it still worked. It should run faster if you're doing it on the GitHub that you pulled from the website. But either way, in these 3 lines, it will just spit out a plot that shows the photon data and an image. And we can totally run this on completely different data. If we just found another URL from OpenAltimetry, we can just throw that in there. And now my code is doing weird things again. And if we wait a little bit for this to download, we can see totally different data. This is just from a different rectangle I drew in OpenAltimetry, essentially, and this just looks at some nearshore bathymetry, something similar to what we saw in the last tutorial. And it really does give you a nice context of what the data actually means that you're looking at here. So in this case, we have some land cover on the start of this overpass, and then it passes over this reef and then drops into the deep ocean. And we can correlate that really nicely with what we see in the data. Something that looks a little bit weird, ATL13 is, which product is that? I think that's the inland water. Like some of these products have geophysical corrections applied already, so they might not completely match up with ATL3, but you could always change that code a little bit to make it fit to your goals. And now we can get to the exercise. Actually, first let me show you this notebook. I made a notebook that has a few use cases. If you just click on this link, it should open that up. And that is already rendered here, but essentially it has a few examples of how to use this code, where it's always just those 3 lines and it shows different data. This is the data from this tutorial that we went through step by step. I also pulled the snow depth tutorial data from earlier today and just ran my code on it. And you can actually see the transect that they showed there, where in the middle, where there was a lot of snow depths in their results, you can see there's actually these flat regions. And if you zoomed in on this, you could actually see there's a lake. So maybe some of this was like related to changes in the water elevation in the lake between the acquisition of the reference DEM and the ICESat-2 data. There's also the other track here where you can see the road that was plowed at the time, which also affected snow depths. And from the bathymetry tutorial also earlier today, actually, I guess Jonathan changed the data. I saw he had something about Japan in there. That was some data that he was running. We didn't get to see this today. I also tried to run it on the data that he showed earlier today, and that actually showed me that in some cases my code breaks. This was a really long ground track, and so here it only found a Sentinel-2 tile that was didn't cover the entire region. So if you run into something like this, my code certainly isn't perfect. I just wrote it for this tutorial to kind of show how to interact with Google Earth Engine. But you could probably fix something like this fairly easily with some mosaicing off the image collection that you returned. So it's definitely not out of the box usable, my code, for everything that you want to use it for. Doesn't come with that warranty. And so on. So there's a few more things that you can look at. And how long do I have for this tutorial? Are we?
Well, we're reaching near the end. But
okay.
If you wanted to do the interactive, we could
Yeah, I think we can probably skip it, but I will just point you all to it. So essentially on the bottom of this thing, I wrote an exercise that essentially just tells you to go into open altimetry, browse some data, maybe zoom in on a region that you're interested in, and just grab a small scale feature ground track that's less than 20 kilometers, ideally, because otherwise this code might break. And then just plot that with the code that I've provided. So that would essentially just be the 3 or 4 lines down here where you enter your own stuff. And I just invite you to, if you're working on something on a tutorial where you want to visualize a certain small ground track, just try running that code and see if you can visualize the data that you're actually using and make some more sense to it. Or if you have some time and are just interested in something that you're maybe using for your research, maybe just try running the code. And if it breaks, also let me know, and I'll see what can be done to fix it.
Hey, Philip, I would suggest we, if it works for you, give folks 10 minutes or so to see what they come up with if they want to play a bit.
Do that.
Yeah.
All right. Yeah.
I think that'd be great. And we could kind of roam around the room, maybe get a couple helpers too, and just see. And we could, at the end of that, see if there's any interesting plots that people discover as they play a little bit. I think that'd be great.
All right. Yeah, let's do that. All right. We have some 10 minutes. Try to find something in open altimetry and run this code with it. And I think what you could do is just download the image that then shows up in your data and drop it in the Slack. Hopefully we'll get some good visualizations.